For years, using computers meant we had to learn their language, code, commands.
Right. It was always on their terms.
Exactly. But something fundamental has shifted. Now, for the first time, computers are actually learning to speak our language.
And that's where large language models, LLMs, come in.
Precisely. So today, we want to go past the hype, really try to open up that quote-unquote black box.
Get to the core ideas.
Yeah, dive into how these things actually work.
Mm-hmm.
Think of this as your shortcut, based on the material you've provided, to getting properly informed.
It's quite a journey, actually. We'll look at the core idea, which is surprisingly simple, then, why scale is so vital, how language gets turned into numbers, this really clever attention mechanism,
Right.
how they're trained, and crucially, what they can't do yet and what's coming next.
Okay, let's start there then, this core idea. Because you hear all this stuff about AI thinking,
Yeah.
but you're saying it starts simple.
Very simple at its heart. Fundamentally, LLMs are just next token prediction engines.
Next token. Like the next word.
Often the next word, or sometimes just a piece of a word, a token. It's all about predicting the most probable next thing in a sequence. But here's the fascinating part. Doing that simple task, predicting the next bit of text, but doing it with incredible sophistication and scale. That's what leads to all the complex behavior.
How so?
Well, take the example. The first person to walk on the moon was. The model doesn't know the answer like we do.
Right.
It just calculates that Neil is statistically way more likely to come next than, say, pizza.
Okay, makes sense.
So it predicts Neil. Then, given the new sequence ending in Neil, it calculates Armstrong is the most probable next token. It builds the answer piece by piece.
Wow.
And somehow, through just doing that, it implicitly learns grammar, facts, context, even style. Because it needs all that to make good predictions. Answering questions, writing poems, translating. It emerges from that core task.
So it's like this incredibly sophisticated autocomplete that ends up looking like understanding.
Yeah.
That's quite something. But, okay, what about the large part, the L in LLM? That's obviously key.
Oh, absolutely crucial. It's
Yeah.
all about scale. Two kinds, really. Model size and data size.
Model size meaning?
The number of parameters. Think of parameters like the internal knobs or connections the model can adjust during learning. GPT-3 has 175 billion of them.
Hell yeah.
Yeah. That massive number allows it to capture incredible amounts of nuance from the data. And speaking of data...
That's the other part of scale.
Exactly. These models are trained on truly vast amounts of text. Trillions of words, scraped from the public internet, books, articles.
So that's where the knowledge comes from.
That's where the broad knowledge comes from. But this scale has a serious cost. Training these massive models takes huge amounts of computing power.
Right, I've heard that.
Millions of dollars. And an enormous energy footprint. It's a major undertaking.
Okay, so huge scale, predicting the next token. But how does a machine, which only understands numbers actually, read? How does Riverbank become numbers it can process differently from bank deposit?
Great question. It's basically a two-step process. First, tokenization.
Breaking words down.
Yeah, breaking text into smaller, manageable pieces, often subwords, like unhappiness might become happiness. It's really efficient. Each token gets a unique number ID.
Okay, so text becomes numbers.
Yeah.
But how does it get the meaning?
That's step 2, embeddings. Each token ID is mapped to a list of numbers, a vector. Think of it like coordinates on a huge, multi-dimensional map.
A map of meaning.
Kind of. Words with similar meanings end up closer together on this map. And the relationships between these vectors can capture meaning. The famous example is that the vector for king minus man plus woman ends up very close to the vector for queen.
Whoa. So the math itself captures semantics.
Exactly. It's how the machine starts to grasp nuance.
Okay, this is getting clearer. But processing long sentences, keeping track of context. Older systems struggled with that. What changed?
The transformer architecture, and specifically its attention mechanism. This was the real breakthrough.
Attention, like paying attention.
Pretty much. Instead of processing words one by one, attention allows the model to look at all the words in the input sequence simultaneously. For each word, it calculates attention scores that tell it which other words in the sentence are most relevant to understanding this word's meaning in this specific context.
So for bank and riverbank, it pays attention to river.
Precisely. And for bank, in bank deposit, it pays attention to deposit. It weighs the importance of surrounding words dynamically. This gives it a much richer, context-aware understanding.
That makes sense. So we have tokens, embeddings, attention. How does this all come together to create the helpful chatbot I might interact with? How are they actually trained?
It's typically two main phases. First is pre-training. This is the massive, unsupervised phase where the model just learns from those trillions of words, predicting the next token over and over. This builds the foundational knowledge, the base model.
Okay, so that gives it the raw knowledge.
Right, but it might not be very good at following instructions yet. So then comes fine-tuning. This is where we shape its behavior.
Oh.
Techniques like instruction tuning, training it on examples of instructions and good answers written by humans, and reinforcement learning from human feedback, or RLHF.
RLHF, that's where humans rank different answers.
Exactly. Humans indicate which responses they prefer, and the model is trained to produce answers more like the preferred ones. This makes it more helpful, harmless, and honest, or tries to.
So understanding this training process means we can get better results too, right?
Yeah.
Through prompt engineering.
Definitely. Knowing how it works helps you craft better prompts, giving it context, maybe a persona, clear constraints, guiding it towards the output you want.
Okay, putting it all together. It's complex but understandable. But it's crucial to remember, these aren't actually thinking, are they?
Absolutely vital. They have major limitations. They hallucinate. They can confidently make things up that sound plausible but are totally false.
Right. I've seen that.
And they can inherit and amplify biases present in that massive training data. So what's next? We're seeing moves towards multimodality, understanding images, video, audio, not just text.
Okay.
Agentic AI, where models can use tools, browse the web, take actions to achieve goals, and a huge push for efficiency, making them smaller, faster, cheaper to run.
Fascinating. We've really gone from that simple core idea of next token prediction all the way to these incredibly powerful, complex systems. It strips away some of the magic, maybe?
It replaces the magic with understanding, I think. Knowing the principles helps you see both the amazing potential and the real limitations. It's becoming essential literacy, really.
It really is. So the question left for all of us, maybe, is as we get better at talking to these systems, what completely new kinds of creativity or new ways of solving problems are we going to unlock?